In space, the most expensive part of any machine isn't the metal, it's deciding to bring it with you. When people hear additive manufacturing in space, their brains tend to jump straight to Star Trek replicators, toss in some raw material, hit a button, and out pops a finished spaceship, hot Earl Grey optional. That's not what we're talking about today. Additive manufacturing is not magic, it is not instant, and it is not a way to skip the hard parts of industry. You can't throw a 3D printer at an asteroid and expect a starship to crawl out overnight, even though you could drop a vial of nanobots on it and expect the same. Nanobots, after all, are a bit like a Swiss Army knife, capable of doing almost anything, but rarely as well or as quickly as a larger, more specialized tool. Additive manufacturing sits in a similar space. It can make an astonishing range of things, but it does not replace traditional industry, and it certainly doesn't outpace it. What it does offer is something more subtle, the ability to make things traditional manufacturing either struggles with or simply cannot do at all. And as we'll see today, many of those advantages become even more powerful in the low and zero gravity environments common in space. That's why dismissing this as just 3D printing misses something important. In space, additive manufacturing isn't about convenience or novelty, it's about survival, logistics, and eventually scale. Space is brutal to supply chains. Every bolt, every spare part, every contingency you didn't think of ahead of time has to be hauled up a gravity well, wrapped in radiation shielding, and paid for in fuel. The farther from Earth you go, the less sense it makes to bring everything with you. And yet the more likely you are to need it. And that's where additive manufacturing earns its keep. Not as a replicator, but as a way to stop launching finished objects altogether. Today we're going to look at what additive manufacturing really is, why space changes its strengths and weaknesses so dramatically, why microgravity makes it both harder and better at the same time, how it becomes infrastructure on the moon and beyond, and finally, how it opens the door to construction at scales rockets were never meant to handle. Just don't expect it to replace factories, it's here to replace cargo manifests. Additive manufacturing is not a printer. On Earth, most manufacturing quietly assumes three things: gravity works, mass is cheap, and factories stay put. Manufacturing in space breaks all three assumptions, which is why additive options matter so much in space. At its core, additive manufacturing is not a specific device, it's a philosophy. A 3D printer is just the most familiar example, the hobbyist-friendly face of a much broader idea, but isn't the entirety of the concept. For most of human history, manufacturing has worked in one of two ways. The first is subtractive. A sculptor starts with a block of stone and chips away everything that isn't the statue. A woodworker takes a plank, saws it down, planes it smooth, turning most of the original material into sawdust along the way. You begin with more than you need, and success comes from removing material with skill and precision. Because this is inherently wasteful, a huge part of our industrial economics is dedicated to finding ways to use or recycle those shavings. The second approach is formative. A blacksmith pours molten metal into a mold, or presses into a shape under a hammer or die. This is fantastically efficient when you want 10,000 identical parts, but it depends on heavy tooling and stable environments. You see this clearly with a candle maker pouring hot wax into a mold. The shape is dictated by the container, and the material flows into it. Yet the same candle maker dips a wick into hot wax over and over to build the candle up layer by layer. They switch to an additive process. The same is true for a potter coiling clay to raise a vessel. Additive manufacturing is not a strictly new invention, but subtractive and formative methods became the backbone of modern industry. Both traditional approaches are incredibly powerful, but they are mass-intensive, rigid, and deeply tied to the assumption that gravity works, raw materials are cheap, and supply chains are close to hand. Additive manufacturing flips that logic around. Instead of starting with a bulk material and carving complexity out of it, additive systems build complexity directly, one layer at a time, from relatively simple feedstock. Wire, powder, resin, or slurry go in. Structure comes out. Many different items can be made from one additive printer, including complex and expensive molds, whereas a mold can only make one item over and over again. And unlike subtractive processes, where most of the material is discarded, nothing is removed unless it absolutely has to be, and intricate internal shapes can't exist without molds, dies, or multi-stage machining. The real shift isn't how the parts are made, it's what gets shipped. If you're operating a spacecraft, a station, or a base far from Earth, you face two very bad options. Launch every spare part you might ever need, or gamble that nothing breaks, nothing scales well. Additive manufacturing offers a third option. You don't launch parts, you launch capability. Instead of a warehouse full of specialized components, you bring raw material and a digital library. The physical payload becomes generic and flexible. The specialization lives in software. A spool of metal wire can be a bracket today, a replacement tool tomorrow, and a structural reinforcement next year. You aren't reducing mass because additive manufacturing is lighter. Often it is, but often it isn't. You're demassing because you're no longer guessing what you'll need years in advance. That difference is subtle but profound. This doesn't eliminate the need to bring tools or critical spares. You still need your basic kit, and a printer won't save you from an emergency happening right now. Printing takes time. What it does save you from is mission failure months later, when something non-urgent but essential breaks and you don't have a replacement. A cracked hydroponics container, the system that's growing your food and scrubbing your carbon dioxide, does not end a mission today, but it quietly puts you on a timer. That's the difference between aborting a mission and improvising your way forward. There's another advantage that matters even more in space, though. Complexity is cheap. In traditional manufacturing, complexity costs time, tooling, and money. Internal channels, lattices, and intricate geometries require multiple machining steps or elaborate molds. With additive manufacturing, those constraints soften dramatically. A solid block and a lightweight lattice with internal cooling channels can take roughly the same effort to print, and in many cases the solid block actually takes longer. In orbit or on the moon, that's a big deal. Strength-to-weight ratios matter, thermal management matters, redundancy matters. Additive manufacturing lets you put material exactly where it earns its keep and nowhere else. That doesn't mean it's fast, though. Additive manufacturing is almost always slower than other mass production. It doesn't compete with stamping presses, rolling mills, or injection molding lines. If you want a million identical parts, additive manufacturing is usually the wrong tool. Again, you'd use it to make the molds, those parts would be made in themselves. But space doesn't want millions of identical parts. Not now, anyway. Right now, it wants a few very specific ones, in places where resupply takes months or years. There's also where expectations need to stay grounded. Additive manufacturing does not turn raw asteroid rubble into precision components without pre-processing. It does not magically refine ores, eliminate impurities, create organic compounds, or bypass metallurgy. It does not ignore thermodynamics, chemistry, or quality control. Printing something badly in space still produces a bad part, possibly a worse one. What it does is allow manufacturing to follow people outward instead of dragging entire supply chains behind them. And that's the thread running through this entire episode. Additive manufacturing is about replacing factories. It's about moving the factory where the problem is, even when that place has no gravity, no atmosphere, and no hope of overnight shipping. Next, we'll see why that's harder than it sounds, and why, paradoxically, space sometimes makes additive manufacturing better at the very things Earth struggles with. The physics of printing in freefall. If additive manufacturing sounds easier in space because nothing weighs anything, that's a very Earth-centric intuition. Microgravity doesn't just take weight away, it takes away a whole set of quiet helpers that manufacturing on Earth relies on without thinking about them. Buoyancy, sedimentation, convection, hot air rising, molten metal settling, particles sinking where they belong. On Earth, gravity does a lot of the cleanup work for us. In orbit, it does not. Liquids do not politely stay put. Heat does not drift away. Particles don't fall out of the way. Everything that was once good enough suddenly needs to be actively controlled or it misbehaves. That's why manufacturing microgravity is often harder, not easier, at least for now. Take metal printing. On Earth, when a laser melts a tiny pool of metal, gravity helps hold that molten puddle in place. In microgravity, gravity is no longer the boss. Surface tension is. The liquid wants to beat up, drift, stretch, or pull itself into shapes you do not ask for. That glowing metal pool becomes the most difficult part of the entire process. Keeping it stable, centered, and predictable turns out to be one of the hardest challenges in microgravity manufacturing. Recent orbital experiments have shown that even small changes in temperature or laser power can send molten material wandering where it doesn't belong. If you lose control of that puddle, you don't just get a bad print, you can ruin the part entirely, or damage machinery nearby. Heat is the second major problem. On Earth, hot air rises and carries heat away. In microgravity, heat just sits there. It builds up. Every print becomes a thermal management problem. If you don't actively move that heat somewhere else, parts can warp, crack, or even partially remelt themselves after they've already been formed. Heat is often a limitation on seemingly magical wand manufacturing process we see in science fiction, and this makes it all the harder. Stuff tends to melt when you do it too quickly because there's always heat being produced when you're making something. In other words, space strips away our manufacturing shortcuts. You can't rely on gravity to settle things, air to cool things, or time to smooth over mistakes. Precision becomes mandatory. And yet, this is where space quietly flips the table. Some materials don't want gravity involved at all. Take optical fiber. Certain specialty fibers, like Zeblan, are extremely sensitive to gravity when they are being drawn. On Earth, tiny variations in density cause microscopic crystals to form inside the fiber, scattering light and ruining performance. In microgravity, those imperfections largely disappear. The fiber can be drawn purer, clearer, and far more efficiently than anything made on the ground. The same pattern shows up in biology. On Earth, delicate biological structures collapse under their own weight. Try to print soft tissue or complex vascular networks, and gravity works against you at every step. In microgravity, those same structures can hold their shape long enough to stabilize. Veins and capillaries don't slump. Layers don't shear. The geometry survives long enough to matter. And unlike most of our other 3D printing examples, this is about making space missions cheaper or more self-sufficient. This is additive manufacturing used to make things for people back on Earth. Things that are rare, valuable, and in many cases, life-saving. That's why bioprinting experiments in orbit have been so promising. Not because space makes biology easier, but because it removes a force biology has been fighting the entire time. This is the real paradox of manufacturing in Freefall. Space strips away the passive helpers we rely on, and it punishes sloppy engineering. Small mistakes matter more, and nothing behaves the way it does on Earth. But if you can control the process precisely, you gain access to material behaviors that are extremely difficult, or outright impossible, to achieve on the ground. And when microgravity becomes more trouble than it's worth, engineers don't just give up and go home. Cheat back. We add airflow where convection is missing. We add rotation where gravity helps more than it hurts. We build small spinning sections, controlled environments, and hybrid systems that give us just enough gravity to behave without losing the advantages of space. Once you understand that, the question stops being whether we should manufacture in space at all. It becomes about where gravity returns, not fully, but just enough to make things complicated. Low gravity, regolith, and the messy middle. Most of the solar system doesn't live at either extreme. It isn't Earth with the comfortable 1G assumptions, and isn't microgravity where everything floats and nothing settles. Instead, most places we're likely to work, the Moon, Mars, large and medium asteroids, small moons, exist in the uncomfortable middle ground. There is gravity, just not enough to behave nicely. And this is where additive manufacturing stops being about spare parts and starts becoming infrastructure. On Moon or Mars, you don't just want to print tools, you want to print landing pads, radiation shielding, pressure holes, walls thick enough to matter. And hauling concrete, steel beams, or bricks from Earth makes about as much sense as shipping sand to the Sahara, so instead we use what's already there. This is where in situ resource utilization, ISRU, comes in, and where additive manufacturing and local geology start working together. Lunar and Martian regolith, the dust and crushed rock underfoot, isn't dirt in the everyday sense, but it is rich in oxides, silicates, and metals, not refined, not friendly, but usable. Rather than shaping it like Earth materials, we have to adapt the manufacturing process to the material itself. One approach is sintering, using concentrated sunlight, lasers, or microwaves to heat regolith just enough for its particles to fuse together. You're not pouring concrete, you're melting dust into something more like ceramic stone. It's rough, brittle, and ugly by Earth standards, but it's strong, massive, and very good at stopping radiation. It also won't blow all over the place and clog all your machinery with razor-sharp dust. This works well for things like landing pads, berms, and structural shells, the kinds of infrastructure where surface finish doesn't matter but mass and thickness do. Another approach uses binders, importing a small amount of polymer or chemical glue from Earth and mixing it with local regolith to create printable composites. This gives you more control and better mechanical properties, but it costs mass. Every kilogram of binder you bring is a kilogram you didn't use for something else. Neither approach is perfect, and that's the point. Space manufacturing isn't about elegant solutions, but acceptable ones. Low gravity complicates all of this. On the Moon, regolith doesn't fall like sand. It drifts, clings, and lofts itself into the air with electrostatic enthusiasm. On Mars, dust settles but slowly, and storms can undo weeks of careful work. On small bodies, you can have enough gravity for material to fall, but not enough to keep it down. Printing in these environments is a constant battle against mess. Dust floats where it shouldn't. Fine and often damaging particles cling to tools, joints, and optics. Excavation doesn't behave like digging, it behaves like pushing against a reluctant cloud. Additive manufacturing here isn't clean room work. It's close to industrial construction in a sandstorm that never quite ends. And it's worse as we get to larger asteroids where gravity isn't a modest fraction but a tiny percent. This is where the cheating comes back. When gravity is helpful but insufficient, clever engineers won't insist on using whatever nature provided. They add just enough artificial gravity to make things behave. One way to do that is with centrifuge printers, fabrication rigs that spin, not to make people comfortable, but to give molten material, powders, and loose regolith a preferred direction. You don't need a full rotating habitat, you just need the printhead, or the build volume, to experience a steady pull while the rest of the facility stays still. And you could potentially do this with linear acceleration too. That lets dust settle instead of float, it lets liquids pool instead of bead, and makes layers stack the way you expect them to, at least once you account for Coriolis force, which again you might avoid with linear acceleration. These systems don't replace microgravity manufacturing or Earth-like factories, they fill the gap between them. And that messy middle turns out to be where most large-scale space construction probably happens at. Low gravity gives you some of the advantages of space: reduced structural loads, easier lifting, weaker foundations, without forcing you to solve every microgravity problem at once. You can build things without fighting their own weight, but still rely on gravity to keep the process stable. Here, additive manufacturing becomes less about printers and more about sites, construction zones, material flows, power systems, dust management, maintenance schedules. Not Star Trek replicators. More like the first awkward industrial towns of a new frontier, improvised, inefficient, and indispensable. And once you're thinking that way, once manufacturing stops being something that fits inside a machine, and starts becoming something that sprawls across the landscape, the final constraint comes into focus. It isn't mass anymore, it's shape. Today we're looking at manufacturing in space, building things in microgravity, where the usual rules don't always apply. But even in those environments, good engineering still comes down to smart design choices at every scale. A great example is the Real Engineering exclusive, The Anatomy of the Nokia 3310, where they CT scanned the iconic cell phone to show how something so simple became incredibly durable, efficient, and reliable. It's a reminder that great engineering isn't always about building bigger, it's about building better. And you're thinking about scaling those ideas up to truly massive construction. My Nebula exclusive this month is Settling Saturn's Rings, exploring how we might turn one of the solar system's most resource-rich regions into a hub for habitats, industry, and megastructures. You can find all of that on Nebula, where every episode of SFAA premieres early and completely ad-free. Go watch The Anatomy of the Nokia 3310 and use my link with a QR code to get 50% off an annual plan. Just $30 for the whole year. Printing at scales rockets can't touch. A rocket can be absurdly powerful and still be a very picky moving van. You can lift tons to orbit, but you can only lift them in the shape of a cylinder within a fairing built to survive launch vibration, acoustic pounding, and atmospheric drag. Even if you can afford the mass, you may not be able to afford the geometry. Things in space can be vastly weaker and lighter too, but they still have to survive being built in Earth gravity and surviving the vastly more brutal g-forces and vibrations of a launch. Space-based manufacturing breaks that constraint in a way no bigger rocket ever truly can. If you can build in orbit, you don't have to pack your structure like camping gear. You can make them the size and shape and strength they actually want to be, not the size and shape the launch vehicle would tolerate, or the strengths to tolerate that launch force. And that changes everything about how we design large systems. Take telescopes. We've been trying to cheat around fairing limits for decades, folding mirrors like origami, deploying petals, using inflatable optics, or assembling segmented pieces like a puzzle. Those tricks work, but they all share the same constraint. Every part still has to fit inside a rocket. But if you can print the framework in space, the framework can be enormous. A light, stiff spiderweb of trusses and ribs, built as a single continuous structure instead of 100 bolted joints. Then you add the reflective surface afterward, not by launching one giant mirror, but by depositing thin films, attached tiles, or growing a mirror layer onto a stable printed backing. The same logic scales to antennas, solar arrays, radiators, sunshades, and habitats. Anything that is naturally wide, thin, and delicate becomes a better candidate for printing or weaving in space than for cramming into a fairing and hoping deployment goes perfectly the first time. The future version of a printer might not be a box with a build plate. It might be a set of robotic tools that crawl along a structure and extend it as they go, like automated ironworkers and vacuum. This is the idea behind concepts like spider fab, a robotic system that extrudes long carbon fiber or composite trusses, then moves along those trusses to extrude more, stitching together larger and larger frameworks. Not a replicator, not a magic factory, more like a spider spinning a web, except the web is a radio telescope, a power station, or the skeleton of a shipyard. And weaving isn't really the right word here. In space, you don't have to build everything as a solid chunk. You can make lattices, tensegrity structures, cable nets, and truss geometries that would be awkward on Earth and natural in orbit. You can build things that are strong precisely because they are mostly empty space, and because you control tension and alignment without fighting weight. That gets us to the part everyone wants to jump to, the self-replicating factory. So let's be careful. No, we're not talking about a von Neumann machine that lands on an asteroid and spits out 1,000 clones of itself by breakfast, all of which do the same by lunch. That's still firmly in the realm of science fiction. Real industry isn't one machine, it's a supply chain. As we discussed before when talking about nanotechnology, there is a path to very real and very useful automation, even down to the nanoscale, but not to anything magical. Manufacturing is a stack of processes: mining, refining, chemistry, high-temperature furnaces, precision machining, quality control, clean environments, replacement parts, and people, or increasingly, a lot of automation standing in for people. But there is a replicator-light version that's both plausible and powerful. You start with a small set of versatile tools that can do rough work: cutters, grinders, extruders, welders, sinterers. Use them to make the things that help you do more work: jigs, fixtures, replacement heads, structural frames, tanks, brackets, conduits. You put the scaffolding for your next machine, and you bring the specialist components you can't make locally: sensors, chips, high-grade bearings, certain catalysts, and you can start making some of those too. In other words, you don't replicate a factory in one leap, you bootstrap it. And the moment you can bootstrap manufacturing in space, you can build solar power systems at the pace of automation instead of the pace of launch manifests. You can expand mining and refining capacity without expanding your launch schedule. You can put mass where it pays dividends, in power, tools, and infrastructure, rather than a warehouse of guesses. That's how additive manufacturing is a force multiplier for everything else we do in space, without ever pretending it replaces everything else we do in manufacturing. Which brings us to the most visceral example: ships. Right now, every spacecraft has to be born small enough to leave Earth, tough enough to survive launch, and light enough to justify the fuel. Even large rockets are still delivering vehicles shaped by atmospheric requirements and fairing constraints, with structural choices driven by stresses they'll never see again after the first 10 minutes. An orbital shipyard flips that on its head. If a ship is built in a vacuum, it can be optimized for vacuum. It doesn't need to be aerodynamic. It doesn't need to handle launch loads. It doesn't need to fit into anything. It can be assembled from modules, printed as a continuous whole section by section, or woven as a truss spine with tanks, radiators, and habitats attached like organs. And because it never lands, it never has to compromise for landing either. Ships like that won't be launched in the way we use the word today. They'll be commissioned, they'll be serviced, refitted, upgraded, and reused. Some might operate for decades or centuries because there's no atmosphere to rust them, no ocean to corrode them, and no gravity to fatigue them the way we're used to. They'll be born in the void and they'll live there, and that's the earned, restrained awe at the end of this story. Additive manufacturing in space won't hand us Star Trek replicators. It won't turn rubble into starships overnight. It won't replace the deep, slow, messy work of industry. What it does is remove the most punishing limit of all, the idea that every complex object has to begin its life at the bottom of a gravity well. It does not replace factories. It replaces the requirement that factories stay on Earth. And once that requirement is gone, the only real question left is not whether we can build big things in space. It's how quickly we decide to, and how big we're willing to go.